Hi again, AP Chem. We are just going to continue on from where we left off yesterday, which means that I'm now starting with factors affecting solubility. So the factors that affect solubility that we're going to talk about first is the common ion effect. And the common ion effect is something that we talked about last quarter with the same chapter, but it's the same concept. It's just now we're talking about that in terms of solubility versus just generally in equilibrium. So what you should see here is that definition that if one of the ions in a solution equilibrium is already dissolved in the solution, the solubility of the salt will decrease. And that should make sense. And then the other note here is that if either calcium ions or fluoride ions are present, in this particular example is what they're referring to, then the calcium fluoride compound is going to be less soluble, right? So let's go ahead and dive right into an example with that. Your first example is, what is the molar solubility of calcium fluoride in now a solution of 0.010 molar calcium nitrate? Okay, so we already dealt with calcium fluoride yesterday, right? So we've been kind of talking about the solubility of calcium fluoride, but now what you can see is we are not adding it just to like pure water. We're adding it to an aqueous solution that already contains this compound, sodium nitrate. And obviously you can tell that the calcium ion is probably going to be your common ion in that solution, right? So you follow the same format. You're going to create your equilibrium expression. From that, you can create your KSP expression. We're still setting it equal to the value you can find in your appendix D. Now when you set up your ICE table, gosh, I hate that happens. I'm sorry. So now when you're setting up your ICE table, instead of starting at 0, 0, you have to start off with your 0.10 value, because that is the value that is associated with this common ion. So therefore, when this is dissolved in the solution, this calcium nitrate, you know you're going to have a 0.01 molar concentration of calcium, and you're actually going to have a 0.02 molar concentration of the nitrate, because there are 2 nitrate ions per every 1 calcium ion that will dissolve in that solution, right? So we're going to start off with those initial values. We're going to add our X. Remember again that I'm adding 2X here for that same exact reason that I just referred to. There's 2 fluoride ions for every 1 calcium ion, right? And so then you get your equilibrium concentration. So now you're going to just solve the equilibrium concentrations like you would before, but now our value is no longer just X, it's actually 0.010 plus X. And fun fact is, we can assume that X is much less than 0.01. So they're pretty emphatic about it. They're like, woohoo, we can just use this value. So you can just use that value. This is one of those cases where you can ignore the addition of X. And then you can just solve, and you should get X equals 3.1 times 10 to the negative fifth. Okay, so that was actually letter A for your example exercise, right? So once again, I'll kind of quickly click through it. You can pause and copy it if you didn't do that as I was going. That's fine. I go kind of fast anyway. So again, what they did is they created an ICE table. We started off with 0.01 because of the concentration of calcium already having a starting concentration based on the fact that it is in a solution that contains the ion calcium, right? And you set that equal to your KSP. You ignore that X value, and you solve mathematically. Just use some basic algebra, right, guys? So letter B for your example exercise has a different, if you want to flip back, it has a different solution, right, or compound that's in the solution. So now you can see we've got sodium fluoride, right? So that means your common ion for letter B is going to be fluoride, not calcium. So they just do that like very quickly, solve for that difference by saying, okay, well now calcium's X, and then fluoride is 0.01 0 plus 2x, right? Still have to keep that like stoichiometric ratio in there. So that just changes your math a little bit. That means this time you're going to have x times this value plus your 2x. Once again, we can kind of ignore x, even though it's doubling in this case, but we're going to get x times that 0.10 value squared. It's equal to your KSP, so all you have to do to solve for x is divide by this value, and then you get your concentration. Okay, so remember though, like what your answers actually are here. That is the molar solubility, meaning again that this is the amount of moles, this 3.9 times 10 to the negative 7th moles of your solid calcium fluoride can dissolve per 1 liter of 0.010 molar sodium fluoride solution. Okay? So at this point, pause, finish 13. Okay? So here are your answers for 13.1. You should have said D. And ultimately, your math should have gotten you 4.0 times 10 to the negative 10th molar for number 2. Okay? All right, so let's move on to factors affecting solubility, pH. Okay, so if a substance has a basic anion, it will be more soluble in an acidic solution. Okay, remember that buffers control pH, right? So when a buffer is used, there's actually no change in the concentration of hydroxide ion. That's like the point of a buffer, right? So what kind of like work are you going to have to do with that concept? It would be things like this. Which of these substances are more soluble in acidic solution than in a basic solution? So, they give you lots of detail here. The problem lists 4 sparingly soluble salts, and which ones are going to be more soluble. Again, another way to word that would be in a low pH rather than a high pH. So we will identify ionic compounds that dissociate to produce a basic anion, as these are especially soluble in acidic solution. So that should make sense. So for letter A, this nickel hydroxide, it's going to be more soluble in acidic solution because of the basicity of the hydroxide ion. So it's going to create an anion that is basic, right? And then the H is going to react with the OH to form water. Okay. B, similarly, this calcium carbonate will dissolve in an acidic solution because, again, the carbonate anion here is a basic anion, meaning like when it's in water, and it will just go ahead and naturally combine with the free hydrogen ions to create carbonic acid, right? And so overall, we're creating this equation. Okay. So let's look at C. What about BAF? Again, fluorine, basic anion, right? Because it's going to create that hydrofluoric acid. And the solubility of silver chloride is unaffected by changes in pH because chlorine is the anion of a strong acid, so therefore it has negligible basicity, right? So fluorine is a basic ion because hydrofluoric acid is a weak acid. Same with these other examples. We're getting all like weak acids as a result of that anion, that free-floating anion. Okay, so hopefully that's making sense for what you need to do there. Remember, if you need extra help, that I'm available, but try out these practices and then just check your work. I'm going to let you finish 14. And here is your answer. So 14 should have been none of the above. And for 14, you'll have to excuse my kind of sloppy handwriting here, but these should be your net ionic equations here. Okay. All right, complex ion formation. So metal ions can act as Lewis acids and form complex ions with Lewis bases in the solvent. The formation of these complex ions increases the solubility of these salts. So what do we mean by these complex ions? These right here, you can tell, are a lot more complex in their formula, obviously. So these are the complex ions that they're referring to, and they give you specifically a Kf value and an equilibrium expression to work with. So this, again, is the type of information that's going to be provided to you. So don't worry about having to figure any of this stuff out, okay? So just real quickly, just as an example of how complex ion formation affects solubility, is in this particular example, you can see that the silver chloride ion is, or I'm sorry, the silver chloride is insoluble. Okay, it has a KSP of, right here is your KSP, and this is like your silver chloride at the bottom for the example. And then in the presence of ammonia, which is what we can assume this liquid is in this test tube here, the ammonia is going to react with the silver, forming silver. Oh, well, this complex ion. I don't know what the name specifically of this ion is, but it's AgN3 2 and then plus, right? So that's going to be forming this complex ion in the solution. So that reaction with the ammonia reduces the concentration of free silver ions and then increases the solubility of silver chloride. Okay, so remember, again, it is insoluble, but because it has this KSP that's really low, you know that there is some dissociation that's happening because it's working in this really like weak equilibrium. But the fact that the ammonia is there in the test tube actually like increases the solubility because it's reacting with some free ions, which is going to mean that that's going to shift the equilibrium. Okay. So the addition of sufficient ammonia leads to complete dissolution of silver chloride. So this is like a magic trick over here, right? This is usually insoluble. It's not going to dissolve in regular water, but when we add something like ammonia in the exact right combination, you can get the dissolution of an insoluble solid. So pretty cool. So let's look at how we're going to evaluate that like mathematically. So it says calculate the concentration of silver present in solution at equilibrium when concentrated ammonia is added to a 0.010 molar solution of silver nitrate to give an equilibrium concentration of, and then you get your concentration of ammonia is 0.20 molar. Neglect the small volume change that occurs when the ammonia is added. Okay, so obviously we're given some equilibrium concentrations, so you can probably guess what's coming. So we're going to see first that we're adding a certain substance to another substance to form a complex ion, right? So if you kind of look back, it says equation 17.22. They're talking about this right here, right? But now we're on the other side of that equation. So we are asked to determine what concentration of silver remains uncombined when ammonia concentration is brought to 0.20 molar in a solution originally 0.01 molar in silver nitrate, right? So what we are looking at, and again, when they're talking, the information that you're looking at right here that's coming in came from this table, okay? So we can see that this is the complex ion that we're talking about, right? Here's the Kf value associated with it, and then here's kind of your equilibrium equation, okay? So what I mean by like we're looking at the reverse of that is we're looking at this kind of breaking apart. So we are reversing the equilibrium equation, right? Do you guys remember what you're supposed to do to the equilibrium like constant when you reverse the equation? Okay, you need to take the reciprocal. Okay, So we're going to say 1 over kf equals 1 over, this is the kf value from the table. And so when you solve that, you get 5.9 times 10 to the negative 8th, okay? So again, like I alluded to, you're going to get they give you this equilibrium concentration of ammonia. So that's kind of where you're solving from. You know your initial concentration of this complex ion is that 0.10 value, right? That's where that came from. You're going to initially start with none of this. And like they're not really interested in the initial and change that happens here because I already have my equilibrium value. That was given to you in the problem, right? So this is going to decrease by a factor of x. This is going to increase by a factor of x. And we know that if this is 2x, that this value should be 0.10, right? Is that what they plugged in there? I guess not. So I think that they want you to solve for this x here and not just make assumptions. So because the silver concentration is small, though, we can kind of make that negligent, or we can ignore that x value, right? So you just enter it into your equilibrium expression. We're going to say x. We're going to say the 0.20 squared, again, because of the 2 in your equilibrium expression, over this value where I have just ignored my x, subtraction of x. And then I set it equal to my equilibrium constant that I solved via reversing that and therefore taking the reciprocal. So you get your x is 1.5 times 10 to the negative 8th. Okay. So the formation of this complex ion drastically reduces the concentration of free silver ions in the solution. So go ahead and finish now 15. Okay, and the correct answer for your solution to 15.1 should be A. And if you calculated correctly, you should have got 1 times 10 to the negative 16th molar for B. Okay, that's all that we're going to do today. Again, I highly suggest finishing up the ARG questions that you have up to this portion of the chapter. We are finishing the chapter tomorrow, and you're mastering tomorrow. Okay, see you guys then.